The next topic is large signal operation. So we have studied in the common mode operation the bias current, that is the bias current that is coming from the VDD is equally divided between the two MOS transistors, right? And in differential mode operation, based on the input voltage VID applied, so the bias current, we are going to have the change in the voltages V01 and V02, and accordingly the drain currents are going to be different. ID1 and ID2, they are going to be different in both the transistors, and depending on the voltage applied, we can even make the total bias current I flow across any one transistor, and the other transistor will be cut off, right? So when Q1 will conduct, Q2 will be off, and similarly, and Q2 will conduct, Q1 is off. So like that, we can make the entire current flow across one transistor. So now we are going to analyze in detail, based on the input voltage VID applied, how the drain current is going to be varied in terms of equations. Okay. So now this is the uh, circuit differential mode operation, and here VG1 and VG2. So the input voltage at the gate is applied as VG1 and VG2, and ID1 and ID2 are the drain currents of both Q1 and Q2. VGS1 and VGS2, it represents the gate to source voltage. Q1 and Q2 are the two MOS transistors. So this is the same circuit. So here we are representing in terms of two input voltages, VG1 and VG2. This is the general circuit that we have drawn in the beginning. So it's a very general circuit. Okay. Now, so you need not draw this. You have the circuit already. Now, so we are going to derive the expression for the drain currents ID1 and ID2 in terms of the input differential signal VID. So VID is the difference between the two input voltages VG1 and VG2. That is the difference between the two input voltages with respect to the gate of the both MOS transistors. So VID is VG1 minus VG2. So assume Q1 and Q2 are perfectly matched. So always for the differential amplifier, both the transistors should be matched and operating in the saturation region at all times, neglecting the channel length modulation and the body effect. So we are not considering the other effects. So we are considering both the transistors are perfectly matched. We are writing these two drain equations, drain current equations. So this equation we have already studied. So for the Q1 transistor, it is ID1 equal to Kn dash by 2 W by L VGS minus VT. So here we are taking in as VGS1 for the Q1 transistor, VGS1 minus VT whole square. Similarly for the Q2, it is ID2, which is Kn dash by 2 W by L VGS2 minus VT whole square. So you know already these drain current equations. So depending on the current, if it is I by 2, we are going to use here ID1 as I by 2. Or if it is I, we will replace the corresponding drain current accordingly. Okay. So please take these equations for ID1 and ID2. Yes. Shall we proceed? So now we are going to do some manipulation on these two equations, and we are going to bring a quadratic equation in terms of the drain current ID1, either ID1 or ID2, and relate with VID, and then plot the characteristic curves, and then find the relation between variation in VID and ID. Now, so these two equations, we are going to take square root on both sides. So 1 and 2, if you take square root, the square term will be removed. If we take square root on both sides, so this is root of ID1 and the root of Kn dash by 2 W by L. So this square is removed. So this we are taking it as equation number 3 and 4. Okay. Now, so now we are going to take the difference between 3 and 4. So 3 minus 4, and substituting for VID as VGS1 minus VGS2. So VID can be taken either as VG1 minus VG2 or VGS1 minus VGS2. Okay, so this equation you can note down, VID equation, this VID equation. And taking this difference, so this will be root ID1 minus root ID2 equal to, so this is a common term, Kn dash root of Kn dash by 2 W by L is a common term, and remaining term we are taking the difference. So it is VGS1 minus VT minus of this second fourth equation, it is VGS2, minus into minus is plus, so this is plus VT. So after this we are going to just simplify. So plus VT and minus VT get cancelled here. and we have VGS1 minus VGS2, which is replaced with VID. So now we have the fifth equation as root ID1 minus root ID2 equal to root of Kn dash by 2 W by L into VID. So now we brought this relation now in terms of VID and the drain current. So you can write down fifth equation. Okay, taking the fifth equation. Any doubts till now? Are you able to follow till fifth equation? You need not write all the steps. You take only the fifth equation. So we have still more steps to bring the final equation. So now this equation is in terms of both ID1 and ID2. Okay. Now we want the either all the equations in terms of either ID1 or ID2. So now we are going to replace ID1 in terms of ID2 or ID2 in terms of ID1. So we know that the total bias current, capital I, it is sum of both the drain currents, that is ID1 and ID2. So totally the ID1 plus ID2 will give the total current I, because it is I only is divided between the two MOS transistors Q1 and Q2. So we have sum of both the drain currents equal to the total current I. Okay. Now, have you taken fifth equation? Okay. Now, the constant current bias, it imposes ID1 plus ID2 equal to I. So we know this total current equal to the sum of the two drain currents. And the previous fifth equation, again we are going to square it on both sides in order to remove this root. Okay, then only we can use this sixth equation inside this. So now we are squaring here the previous equation. So if you square, again it is just expanded. So this is a minus b whole square form. So a square minus b square, sorry, a square plus b square minus 2ab. So this form we are just expanding. So id1 root will be removed. So it becomes id1 plus id2 minus 2 root of id1 id2 on the right side. So it's just a square term. So this root of Kn dash W by L, root is removed, VID is squared. And now, so this we are replacing this ID1 plus ID2 as the total current I. And so this Kn dash term is brought to the left side, and the root 2 root of ID1 ID2 is taken on the right side. So this is made as seventh equation. Okay. So you need not write this one. You take the final equation. So you're able to follow this up till the seventh equation. Able to understand? Just we are doing some simple manipulations. So ultimately, we are going to bring it into a quadratic form. Okay, and we are going to find the roots for the drain current. Any doubts till this? Just try to understand the flow. If you want, you can leave some space. You can fill it later. But there are. I'm just giving all the steps in detail, so you need not write everything. Able to follow till seventh equation? Shall I proceed? Yes. So now in this ID1 and ID2, we have two drain currents. So either we want in terms of ID1 or ID2. So we are going to write ID2 as I minus ID1, right? So we know already ID1 plus ID2 equal to I. So ID2 is replaced as I minus ID1, and then square on both sides of the previous equation. So now we have replaced inside this root into. So we are squaring both sides. So this becomes this is square, and here it becomes 4 ID1 into I minus ID1. So we are expanding this as 4 ID1 into I minus 4 ID1 square. So now we are having a quadratic equation. So you see here, first term, it is ax square. So this x you consider as a variable, which is in terms of ID1. So this is ax square plus bx. So this is 1 or minus. So b is minus 4i, which is the coefficient. ID1 is the variable, and this is the constant term. Constant term. So it is of the form ax square plus bx plus c equal to 0. So which is a quadratic equation. So now we are going to solve for the roots. Minus b plus or minus root of b square minus 4 ac by 2a. So that equation we are going to use and solve for ID1. So this we are going to take it as 8th equation, and this is of the quadratic equation of the of ID1, variable ID1, which can be solved for ID1. So now we are solving this equation. So substituting the quadratic equation root, and so just after this we just simplify this, and finally we're going to have I by 2 plus or minus 1 by 2. So this is just again inside we are simplifying. Finally, further simplification, we are having ID1 as I by 2 plus or minus root of k and dash w by l into I. Then here this 1 by 2 is brought here, VID by 2, and inside this root of 1 minus VID by 2 whole square by root of I by k and dash w by l. So this is the final equation in terms of ID1. So we have solved for ID1 the quadratic equation. Okay. So previous all these steps are simple math. Okay. So just if you just simplify, go inside, have a look, and you can understand. Okay. So we have just solved for ID1. So it is this is I by 2 plus or minus this. So now we can take this ID1 as I by 2 plus or minus some incremental current. So this total term can be taken as some incremental current. So we know that I by ID1, it is incremented by I by 2 certain amount. At the same time, ID2 will be decremented, because when you add ID1 and ID2, it should be equal to the total current I, right? So ID1 is incremented, at the same time ID2 is decremented. We can take ID1 as I by 2 plus of this term, the entire term, the previous this equation. We can take ID1 as I by 2 plus this term, ID2 as I by 2 minus of this term. So we have two roots here, plus term and minus term, I by 2 plus term and minus term. So we can take ID2 as I by 2 minus of this term. Okay. So finally, we got this relation, the 9th and 10th equations. It represents the relation between the drain current ID1 in terms of VID, and similarly ID2 in terms of VID. Okay. So after this, we are going to we are going to now plot the characteristic curves in terms of VID and ID1 and ID2 by varying the input voltage. VID is going to be varied over the range minus root 2 times of the overdrive voltage to plus root 2 times of the overdrive voltage. So we have studied in the previous class. That is the operating range, min to max, right? VID min to VID max. We are going to vary the VID and observe the variation in the drain current. Okay. So you can write down 9th and 10th equations.
Ma'am, why did we drop the minus sign for ID1?
Yes, which minus?
It was plus minus this whole thing, no?
Yeah, plus or minus. ID1 was plus or minus. See, okay. Otherwise, you can even take it like this. So this ID1 is I by 2 plus or minus, right? So I'm taking the first root, which is plus, right? And so we can take the sum of ID1 and ID2 equal to I. So I can write ID2 as I minus ID1. So if you just take the I minus I by 2 is what? Of this total term. So it will become again I by 2 minus of this. So if you add both, it will become I. If you just add 9 and 10, what will be the output? It will be equal to the total current I. So this plus and minus term will get cancelled. So I by 2 plus I by 2 will become I. It will
Ma'am,
be
for
equal to the
ID1,
total current. Yes.
that means that ID1 has two values and ID2 will also have two values?
No, ID1 has two roots as of now, as since we have solved for the quadratic equation. But in the analysis, the value of ID1, the other root will be equal to ID2.
Okay, thank you.
That deviation, negative deviation, will be equal to the other drain current.
Yes, ma'am, got it. Thank you.
Okay. Yes. Yes. Okay, have you taken this equation? Now this equation we are going to rewrite in terms of the overdrive voltage. Okay, so we know what is the relation between overdrive voltage and I k n dash by, w by L. So we can write this root of I by k n dash w by L as the overdrive voltage. So inside this root term, we are going to replace this I by k n dash w by L as the overdrive voltage, and also similarly here inside this root term, we are going to manipulate. So here this we have I as a product, so we can multiply and divide by I and bring in terms of the overdrive voltage. So now, so at the bias point when VID is 0, so we have ID1 and ID2 equal to I by 2. So here in this equation when VID is 0, we will have the ID1 and ID2 equal to the half of the bias current. So have you taken 9 and 10?
Yes.
Okay. Now in this, we are going to rewrite in terms of, so at the bias point VGS1 and VGS2 equal to VGS. So we are going to rewrite this 9 and 10 as 11 and 12. So in terms of the overdrive voltage. So you see here in this previous equation, we are going to multiply and divide by I. So this becomes I by the overdrive voltage. And in this second term, so we are in the denominator, we had I by K n dash W by L inside this root. So we are replacing as by VOV. So this is our final equation, 11th and 12th equation. So this equation now we are going to plot in terms of ID1 and ID2. So these two equations describe the effect of applying a differential input signal VID on the currents ID1 and ID2. They can be used to obtain the normalized plots ID1 by I and ID2 by I versus VID by VOV. So here we are normalizing the drain current with respect to the total bias current, and the input voltage VID is also normalized with respect to the overdrive voltage. So we can see here, this is the characteristic curve that is obtained. So from this curve, we can make all final. We can it serves many purpose. So we can infer many things here. You can see VID is the input voltage which is varied from min to max range. That is minus root 2 times of the overdrive to plus root 2 times of the overdrive. So and this is the operating range. And when VID is 0, when VID is 0, you can see the value of ID1 and ID2 equal to I by 2. So this is I, so I is 1. So I by 2 is 0.5. So at VID is 0, the value of ID1 and ID2 will be equal to 0.5, or it is I by 2, right? And now I'm going to vary VID over the positive range. That is when VID will be positive. VID is positive. This is the value of ID1 by I. We are normalized with respect to I. So the ID1, the drain current of the Q1 MOS transistor, it increases. At the same time, ID2 by I, it decreases in order to compensate for the total current. So if you add both these currents at any point, it will be equal to the total current capital I. It will be equal to the total current I at any point. So when ID1 will increase, ID2 will decrease at the same time. Similarly, on the negative side when VID will be negative, ID2 will increase. It means Q2 transistor is operating and Q1 is cut off. Here on the positive side, Q1 is operating and Q2 was cut off. And now when VID is in the negative range, ID2 is increasing. At the same time, ID1 is decreasing. In order to maintain the total current, ID1 plus ID2 equal to capital I. Okay, so this is what we infer here. So I'm just giving you in brief. So when VID is 0, total the both the drain currents will be equal to the half of the bias current. In the positive range, ID1 will increase, ID2 will decrease, and this total current will remain the same. And in the negative side, when VID is less than 0, ID2 will increase, ID1 is decreasing, and the total current will always remain the same. Okay, this is what we infer from this large signal analysis. Okay, so you can draw this plot roughly, and you can write these points which are inferred. See, all these equations will be used in using the numericals. Okay, so please, I suggest you to make a note of all these equations. Most of the equations will be using for the numericals, because you have to understand the analysis first, then only you can apply clearly in the numerical. Okay, so now when VID will be equal to the root 2 overdrive, that is when VID it reaches its maximum, then the capital I will be totally equal to the drain current 1. So I is totally steered in the Q1 transistor. And similarly, on the negative side, when VID is the negative minimum minus root 2 VOV, then I will be equal to the total drain current ID2. So it is then Q2 is working. Here on the right side Q1 works, left side Q2 is working. The transfer characteristics are absolutely non-linear because of the term VID square. So see here in this equation that is final equation, or even this 9th and 10th equation, you can see here this VID, we have a second term which is VID square. So because of the square term, that the curve is slightly non-linear. The variation is non-linear because of the square term. Okay, so in order to improve the linearity of the system, we are going to neglect the square term, and we are going to limit this equation 11 and 12 with VID alone. Okay, so we are going to have VID as small as possible in this in order to improve the linearity. So the transfer characteristics are absolutely non-linear because of the term VID square. To obtain linear amplification from the differential pair, make VID as small as possible. So for a given value of the overdrive, keep VID by 2 much smaller than the overdrive voltage, which is the condition for small signal approximation. So in order to have a better linearity of the differential amplifier, we are going to have this input voltage VID by 2 much smaller than the overdrive voltage. So our equation, the previous equations for the drain current, we are going to limit like this: ID1 equal to I by 2 plus I by VOV into VID by 2, and ID by 2 equal to I by 2 minus of this. And so let us take this as ID. So this is ID. So this ID1 it increases by ID2 it decreases by ID. So you can take this final equation. So this is the approximated equation for small signal approximation. That is, we have neglected the square term. Have you taken this equation? Final equation for ID1 and ID2?
Ma'am, 1 minute.
So this is one way to improve the linearity of the differential amplifier. There is one more alternative to improve the linearity, is to increase the overdrive voltage. So either we can reduce the VID, or we can increase the overdrive voltage. So this overdrive voltage can be increased by doing the manipulation in the hardware. That is, the width to length ratio has to be increased in order to increase the overdrive voltage. So we can see here the linearity can be increased by increasing the overdrive voltage of Q1 and Q2. This can be done by using smaller W by L ratios, width to length ratio. So improved linearity can reduce the GM. So since this relation we know, GM equal to 2 ID by the overdrive. So if you increase VOV, it is inversely proportional to GM. So GM can reduce. So in order and hence the gain can reduce, because GM is proportional to the gain. So now we have to have proper care in order to have balance between the overdrive voltage and the VID. So VOV can't be too high, or VID should be less. So this equation we have already studied, GM equal to 2 ID by VOV. So these are possibilities to increase the linearity of the differential amplifier. So this is the nonlinear term. So whenever we want to calculate the nonlinear term, we can use this equation. So this VID by 2 by VOV whole square. So this is the nonlinear term we'll be using uh, to calculate the nonlinearity of the differential amplifier. Okay, so you can refer 11th and 12th equations later. I think I didn't give you time to write this equation, which is inclusive of the square term. Okay. This is the analysis showing the variation between the input differential signal and the output drain currents ID1 and ID2. Okay. So any doubts? I will stop here for today. We will do some numericals based on this in the next class.